While others are filling out the forms, you have a chance to ask an astrophysicist any question you like. And as we like to say, there are about 6 billion people in the world. There are about 6,000 professional astrophysicists, so it's a 1 in a million chance that you meet one. So if you have an astronomy question to fill in the time before we start, I'm happy to make up an answer. And sometimes it might even be the truth. Yes?
Actually, if you don't mind, how did you become an astrophysicist?
Okay, so the question is, how did I become an astrophysicist? It's by accident, somewhat. Okay? When I was in second grade, I loved to show off by adding huge tables of numbers. I was always the math geek, okay, who could do the math problems that nobody else in the class could do. And I said, oh, well, then I'll be a mathematician, and had no bloody idea what a mathematician was. And as I got to older grades, I found that what was really cool for me was the word problems. Okay, the physics word problems, which everyone, how many people hate the word problems? Be honest, come on. A lot of people sit there and go, oh my God, these word problems. Jack is leaving here, and the train is going there, and then a bee flies across here, you know, and that was what was cool to me. So it was the problems of mathematics that really excited my attention. So I did my undergraduate degree in physics. And after I got to the upper levels of physics, I found that, you know, the really coolest problems in physics were in astronomy or in astrophysics. Because if you think about it, these are objects that are millions to billions to trillions to quadrillions of miles away. And we cannot take a nebula into the laboratory, slice it up, dice it up, open it up, look at it. We can only tell what's going on via the light that comes from these very distant objects. So just from the light that we get from these objects, we have to figure out what the heck is going on these quadrillions of miles away. That was a really cool problem, okay? I mean, that is a detective story. It's a, you know, it's your Sherlock Holmes deduction, you know, taking it to the extreme, where you only have the light from it. So I did my graduate degree in astronomy, and from there I found I found a thesis advisor who was doing computer programming. So I actually did computer simulations of galaxy formation for my PhD thesis. So it was mathematics to physics to astronomy, and then moving into a whole a range of things within astronomy in terms of the computer simulations. And I've done a lot of visualization that comes out of my simulations. And then after doing that and doing an IMAX film with my PhD thesis, I was pulled into the American Museum of Natural History to be a curator for the opening of the Rose Center for Earth and Space in 2000. And then I came to Hubble after realizing that my kids were going to start elementary school and we wanted them to grow up in suburbia. So it's all throughout my development, it's been a sideways motion. Going, oh, I'm going this path. No, let's step sideways. Oh, I'll go this path. No, I'll step sideways here. And, you know, it's finding the path that really suits you. And so when I talk to kids, I say I wasn't a kid who looked up owned a telescope at age 6 and, you know, always, you know, always had his head in the stars. It's just been a sideways motion throughout my career. Okay? Any other questions? Yes?
Have you got to work with the Voyager project?
No. Voyager was in the 1970s when I was in, I was in middle school when Voyager launched. Okay, so, but I've talked to people who've worked on it, and of course we've seen, the data from it is incredible. Actually, I think the Voyager project was probably one of the milestones of modern astronomy. It changed our view of the solar system more than any other project because these little dots of light became real worlds. And, you know, I did a DVD course with the teaching company, and they asked me what was the most significant milestone in understanding of the solar system. And most people would point to Copernicus, putting the sun at the center of the solar system, which was a philosophical shift. But a real visceral shift was the space age, and Voyager in particular, that changed our solar system from just being these little dots moving across the sky to being real places, the pictures that you see on the walls around you, okay? That was, the space age truly transformed it made it from being just, out there to being something that we could really look up close and personal. Okay, so Sten Odenwald, I assume, talked about black holes, and he's talking about Andrew Hamilton's group at the University of University of Colorado at Boulder, which actually I'll be there tomorrow. I'm flying out tonight to go to Colorado and visit the Fisk Planetarium at Boulder. And Andrew Hamilton is the one person I know of who would have a chance of making a scientific argument that we could understand what's going on inside a black hole or through a wormhole. So he is in my knowledge, and I'm not the most knowledgeable about black holes and black hole science, but he's the one person I know that I have a personal relationship with that I could say, yes, he's the one who could. Now, traditionally, basically, we say black holes have no hair. Okay, did Sten talk about the no hair theorem? Okay, black holes have no hair. They have no properties other than mass, charge, and spin. Okay? You can't say anything. You can't say what color it is. You can't say how long its hair is. You can't say whether it woke up on the right side of the bed this morning. Okay? Black holes have 3 properties, and that's it. And from the outside, that is true. But we don't know what happens on the inside. And so you can speculate what happens on the inside. But it's a bit in the realm of metaphysics, like speculating what happened before the Big Bang, right? Because the phrase "before the Big Bang" doesn't quite make sense. If time began at the Big Bang, how could you be before it, and other things like that? Okay, so I don't know enough to say that to say that, but the extrapolation into the event horizon and beyond it, I do know that if you were on a spaceship passing into the event horizon, for a large enough black hole, a supermassive black hole, you wouldn't even notice passing into the event horizon. It's just that information can't propagate out. So we can speculate on what is happening inside it. The problem is that testing that hypothesis is very difficult because the information doesn't propagate outside the event horizon. Okay? So whereas they can come up with some really good ideas, I'm not sure how they would test them, just like string theory. How are you ever going to test something that's 10 orders of magnitude below what we can observe? There's a lot at the gray area at the edge of research that, if we're totally honest, we're saying, yeah, we're getting really good ideas. It's the testing of it that's more difficult than that. All right, so I am Dr. Frank Summers. You can call me Frank. You don't have to call me doctor. I just put it up there because, well, it works to say, hey, I have a PhD. Woo-hoo. Doesn't matter. I got what we really have is we're up at Space Telescope, and we got lots of cool ideas of what's going on in the universe from Hubble. This light is bothering me. Well, no. The point is we do astronomy, and astronomy has a lot of black. And if there are lights on the screen, thank you very much. It's hard for you guys to see all the cool stuff that we've got. So my talk is a sneak peek at the first billion years of the universe, and it's about a cool project called the Frontier Fields that is just starting up on Hubble. Actually, it started about 9 months ago. I'll show you some of the first results, and I will show you how we can go better than Hubble. Okay? And you say, wait a minute, Hubble is the ultimate. Yes, we can go better, and it's a really cool trick. All right, so first, what we have to do is we have to talk about looking deep. I can gaze deeply into your eyes, right? And I can mesmerize you with that, right? But what we really want to do is we want to gaze deeply into the universe. So here's a 1-minute exposure of something in the universe. And if you know what it is, keep it to yourself. Those of you who don't know what it is, I want you to guess. Okay? You have a good look on your face, like you're inquisitive. Give me a guess as to what you're seeing on the screen here. Yes, I know. I'm going to put you on the spot. But then again, you're here to learn, right?
I don't know.
You don't know. Just describe it. Any words?
A bright spot.
A bright spot. Thank you, okay? I accept simple answers like that, okay? How about you right here? Do you have anything more than a bright spot?
Nope.
Okay. Yes?
Is it a Messier object?
It is a messy object, yes. Okay? I'm not going to tell you whether it's a Messier object, but it is a messy object, okay? All right, so you obviously have some astronomy behind you, all right? So you'll be able to guess it. All right, keep it to yourself until we get to the 45-minute review. All right, so we see a blobby thing here. What else do we see? Right here.
It's bright.
It's bright. Okay. What else? Things that look like stars. These points, right? Okay. You know, some people overlook the obvious. Okay, that there is one blobby thing in the center, but there's also all these starry things. Is there a third thing since you're sitting up front?
There's another brighter object.
There's another brighter object there. Okay. Can we tell what these objects are? You can make a guess. That gentleman over there, you know, is already going, I'm thinking Messier catalog, okay? Charles Messier was an astronomer in the 1800s, late 1700s, I believe, right, who cataloged a lot of objects in the sky. Yes, it will turn out to be a Messier object. All right, so we've got a blob, another bright thingy, and lots of stars. All right, well, if we expose now for 5 minutes, what do we get? A bigger blob. Very good. All right. We still have the stars here. We still have this bright object. Let's go back. That bright object gets just a little bit brighter. The blobby object gets a bit blobbier, right? Okay. Now let's expose for 30 minutes. Now we're starting to see something. Okay. In the pink there. You just shook your head. I know. Oh, my gosh. I reacted, therefore I'm going to get called on.
No, that's fine.
What do you see?
Well, I think I know what it is.
You think you know what it is? Okay, we'll leave that for the next slide. Okay, next slide you can say what it is. Okay, but what do we see in addition to the blobby?
I'm starting to get a sort of spirally shape to it.
A spirally shape to it? Okay, I'm seeing that there's sort of a darkish thingy here, right? Compared to relative to the brightish thingy around here, we're getting an ovalish shape here, and then we're getting these lanes of darkishness, right? Okay, which is it's kind of hard to say dark stuff when you're actually looking at an exposure, right? But it's dark by contrast, of course, as opposed to being bright. All right, do we still have the stars? Okay, do we still have that thing down here? And that thing down there, has that changed much? Yeah, who said yeah? Okay, how has it changed?
A little bit bigger and brighter.
Bigger and brighter, but basically same sort of shape, okay? Not quite as blobby as this one up here, right? Huh?
It looks like the first blobby thing at 1 minute.
It looks like the first blobby thing at 1 minute. Okay, so keep this in your mind. Let's go back, tick, tock. Okay? Although I will say that the first blobby thing at 1 minute even had a little bit of fuzz around it, right? Okay, so there's a definite difference between this thingy and this thingy in terms of the fuzz. All right, but we go 5 minutes, we go 30 minutes, and let's do it all right, and 45 minutes. Boom! Ooh, okay. So the gentleman who knows it's a Messier object, which Messier object is it? Do you know? What?
Don't know.
Doesn't know. All right. In pink, you said you thought you know what it is.
Well, is the blue,
The blue is an artifact of this up here, the projector, which is misaligned in its blue gun. Okay. So you see that blue shadow here? That's not real. That's the projector having problems. I'm sorry about that. I can't control that. Okay.
Andromeda?
M31 Andromeda, yes, this is Andromeda, okay? But what I really like about this sequence is it shows you as you look longer, you look deeper into the universe, you see more stars. Watch those stars, okay? From here to here, you don't get many more, but boom, look at all the stars that appear. The fainter objects that you get to see as you look deeper, okay? The more detail you get to see in objects. This is why astronomers want to do very long exposures, okay? And Hubble has done some really long exposures. Yes?
So nothing's changing about those pictures except time?
Time, yes. This is the exact same camera from the National Optical Astronomy Observatory. Yes?
As it's being exposed, is it tracking?
Huh? Yes. For 45 minutes. Of course, the Earth is turning, right? We usually think of the night sky moving across the sky. It's actually the Earth turning, right? And so we have to track an object as it moves across the sky. In 45 minutes, it will move, about 10, 15 degrees, right? Maybe 12 degrees. It'll move in 45 minutes. So we actually have to follow it while it moves for over 45 minutes, okay? All right. So this is a modern image of the Andromeda galaxy, all right? This is that blobby thing, which is a satellite galaxy of Andromeda, NGC 205, if I remember correctly. This is M31, and this is M32, which is another satellite galaxy of it. Okay? So, the point being that we really like to take deep exposures to see fainter things. All right? The other point to make is that fainter things will also generally be more distant. Okay? Fainter objects tend to be more distant simply because if I have the same brightness here in front of you and the same brightness over here, well, then this is going to appear fainter. All right? So a star that's nearby will, of course, appear brighter. Apparent brightness will be higher if it's close. Same is true for galaxies. So Hubble has done some deep observations, and the most famous, the first observation it did, famous observation, is called the Hubble Deep Field. And so the Hubble Space Telescope is a very valuable resource. And in 1995, the director of the Space Telescope Science Institute, Bob Williams, basically did a career-risking move. He said, let's do a really deep field staring at a blank patch of the sky. Let's look at nothing for an entire week. Now, a week's worth of Hubble time is absolutely incredibly valuable. At this time, Hubble was oversubscribed by a factor of 11 to 1. We had 35,000 orbit requests. We only had 3,000 to give away. Okay? And then we're going to take 100 of those orbits and look at only one spot in the sky. It was kind of crazy, but we had this incredible piece of technology that had better view than any other optical telescope. He wanted to see what we could find. Could we see very small, very distant things? So, in this patch of sky off the handle of the Big Dipper, right there, we're going to zoom in. This is 26 degrees field of view. Zoom in to 5-degree field of view. Zoom in again to a 1-degree field of view. Zoom in again to a 14 arc-minute field of view. And zoom in again to a 3 arc-minute field of view. 3 arc-minutes across. This is the patch of sky they stared at for basically a week. You can see one blobby thingy and another blobby thingy. Very faint. This is what the Digitized Sky Survey sees in this point field of view. Hubble, with a week's worth of integration time, got that. Kind of cool. This blew us away in 1996 at the AAS meeting in Austin, Texas. I was there, and they put up a 8-foot by 8-foot poster of this, and everybody just stared at it because we had never seen this deep of an exposure of the universe and seen the small, faint objects that Hubble could see. Most of these objects would be blurred out by ground-based telescopes. So here is the Hubble Deep Field, 1996, and it was taken with a camera called WIFPIC 2. That'll play into our story in just a minute. So if we zoom in, we can see that we have some large galaxies, okay? Larger would tend to be closer by, simply because, if you take the same size object and you put it further away, it'll tend to be smaller. Okay? Brighter tends to be closer. All right? So fainter and smaller tends to be further away. All right? We've got some large objects, we've got some medium-sized objects, and we have all sorts of small little objects. In this tiny patch of sky, Hubble found about 3,000 galaxies. And we were able to study them with unprecedented detail and at unprecedented distances. So we saw things that look like our normal spiral galaxies, okay, a little bit fuzzy because they're actually billions of light years away. Okay, we saw things that look like elliptical galaxies. The small dwarf galaxy around Andromeda is an elliptical. All right, these just have these fuzzy oblong shapes to them. But what we really saw that was what was interesting was these irregular galaxies. Okay, here are 4 flotsam and jetsam galaxies, I like to call them. One of the astronomical term was chain galaxies because you can see it's a blob and a little bit of connective tissue, a blob and other blobs. So chains of blobs across the sky. And following on to what we did with the Medium Deep Survey in the mid-1990s, we showed with the Hubble Deep Field that as you went farther out into space, you saw more and more of these irregular blobby galaxies. The morphologies of the galaxies changed as you looked deeper into the universe. Kind of cool. Well, that was a huge success. Bob Williams did not end his career. He did not get fired. He actually voluntarily retired a few years later. But it was a huge success. And so we followed it up a few years later with the Hubble Ultra Deep Field. Okay? You got to give it a new name so that everyone knows that it's even better. And those of us who grew up with Ultraman, hey, this is, This is a throwback to our childhood. Right. Why could we do the ultra deep field? Because Hubble is serviced by the space shuttle, and you can see Goddard Space Flight Center there in the cargo bay of the shuttle. This is Hubble in the cargo attached to the Lazy Susan in the back of the cargo bay. And in 2002, servicing mission 3B, we installed the Advanced Camera for Surveys. ACS was an improved instrument. It had an extra decade of technology development compared to with PIC 2. All right, so it had a slightly larger field of view. It had better resolution across the entire detector. It had more pixels. It had increased sensitivity per pixel, and it had improved optical coatings, which meant the throughput of the light. All right, it's very important to coat your optics so that as much of the light goes through the lens, not as much light gets bounced off the lens. So with all those improvements, ACS had about a factor of 10 more discovery potential, we like to call it, for seeing objects. Was there a question? Yeah.
Moon in the background?
No, that's Earth in the background. Yes, because the space shuttle actually turns upside down. So, so you're actually seeing Earth above the space shuttle. Really cool stuff. All right, so in 2003, we went out and we did a lot of observations, and in 2004, we released the Hubble Ultra Deep Field. Okay? Looks a lot like the Hubble Deep Field, but because of the better resolution and the higher throughput, we can see a lot fainter objects and they are a lot clearer. So if I zoom in, you can see that we can see these same big galaxies, but we see them clearer because of the better resolution of ACS compared to with PIC 2. All right, we see again these medium galaxies. Again, we see these small flotsam and jetsam galaxies, okay, all of the distant galaxies. So the same statistics started to show true for the Hubble Ultra Deep Field, but even more, we had better understanding of it. Now, I'm going to show you some of the most distant objects that were observed in the Hubble Ultra Deep Field. These are absolutely amazing. They are incredible. They are red dots. But they're really cool red dots, okay? You got to understand me just how cool these red dots are. All right, some of the most distant objects in the universe, little red dots. Okay, let me explain to you why they're red dots. First of all, this is the only thing that George Lucas got scientifically right in Star Wars, okay? A long time ago in a galaxy far, far away is correct. Why is it correct? Because if I'm the Hubble Space Telescope and he over there is a distant galaxy, the light from that distant galaxy is going to take time to cross the intervening space before I see it. And for very distant galaxies, to travel all this distance is going to take not millions of years, but billions of years. You didn't know you were billions of years old, did you, Dave? Dave is now billions of years old because the light takes a billion years to travel to me. All right? Now, for a galaxy, a million years is nothing, okay? Our sun takes about 250 million years just to orbit the center of our galaxy. Hundreds of million years, nothing. Billions of years, well, that starts to get 5 or 6 or 7 billion years. Now you're talking some serious time, okay? And galaxies actually change over time, as evidenced by this diagram. We went into the Great Observatory's Origins Deep Survey, and we found spiral galaxies that were roughly face-on. And so out to 3 billion light years away, 3 billion years ago, galaxies have their normal spiral shape. They look pretty much like galaxies around us. So 3 billion years, they look reasonable. If you go from 3 billion light years to 7 billion light years, you can see that, okay, well, this one looks nice, but these guys, well, they're spiral structure, but it's kind of ratty, all right? And then if you go 7 to 10 billion light years away, 7 to 10 billion years ago, you can see the cores of the galaxies are there. There might be some spiral structure developing. They're in the process of developing their structure. So if these are the adult galaxies, these are perhaps the teenage galaxies, and these would be your elementary school galaxies. Okay, these would be your kids. We look out into space, we look back into time, and we can see the history of galaxy development. That's really cool, okay? Nobody else can do that. History professors would give their eye teeth to be able to look out into space and see the Battle of Gettysburg or something like that, right? They can't. we can, as an astronomer, I can see what young galaxies look like. I can actually study the evolution of the universe by looking out into space and back in time. That's really cool. But the most distant galaxies in the Hubble Ultra Deep Field are up here, and they are the very young galaxies, all right, the toddler galaxies, that only have the cores. So they are small dots because we're seeing them when they are just beginning to form. Okay? They're the really young galaxies, the toddler galaxies that just have their core and will slowly develop over time into their full, complete structure. But why are they red? Matter of fact, why are these guys white, these guys yellow, and these guys red? Okay? This is another reason, has to do with something called cosmological redshift. Okay? So, the basic idea of the evolution of the universe is that the universe is expanding. Okay? We look out in all directions, we see galaxies pushing away, appear to be moving away from us. We interpret that as not the galaxies moving through space, but space itself expanding. Now, this is a really important point. It's not galaxies moving through space, but the space itself that is expanding. All right? If it were galaxies moving through space, then we would have to be at the very center. We would have to assume that we are special. We're at the exact center of the universe. And I think a guy named Copernicus taught us that that wasn't a really good idea to assume. Instead, if we assume that space itself is expanding, then every galaxy sees every other galaxy moving away from it. On large enough scales, if you're the Andromeda galaxy, you see all galaxies moving away from it. And you're the Whirlpool galaxy, you see all galaxies moving away from it. Over there, you're M87, M87 sees all the galaxies moving away from it. They all see what we see if we make the assumption that instead of moving through space, it's space itself expanding. Okay? Now, when space expands, the light traveling across that space expands with it. And this is what's going to produce cosmological redshift. Here's a little animation to try and get that idea into your head. This grid here is to represent space. We've got a light bulb emitting a blue light, wavelength light, and we've got Hubble. All right? And so when we start the animation, that blue wavelength starts traveling across expanding space. It becomes stretched as space expands, and by the time Hubble observes it, it's in the red. Let me play that for you one more time. Starts out as blue light. The expansion of space stretches it. By the time Hubble observes it, it's red. So the longer the light has been traveling across expanding space, the more the wavelength will be stretched. This is what we call cosmological redshift, because longer wavelengths are at the red end of the visible light spectrum. Okay? Due to the expansion of space, all wavelengths get longer. They move towards the red end of the spectrum. Okay? Hence, the most distant objects, the ones that have been traveling across expanding space for the longest amount of time, become stretched the most and will appear, therefore, the reddest. So, yes?
Does that mean that light will lose power?
Huh? The energy of it, yes.
Energy of light loses
Yes.
power as it stretches?
Right. As you stretch the light, the wavelength goes up, the energy goes down. What's new? C over lambda, right? Okay? That's a physics joke. If you don't get it, don't worry about it. But obviously, so the energy is proportional to the wavelength. All right. So these red dots are, I hope you appreciate how cool these red dots are, because you're seeing early galaxies whose light has been stretched while crossing space. All right? That's why the most distant objects in the universe are these red dots. But, okay, you're thinking to yourself, wait a minute, that can't, wait a minute, it doesn't end at the red end of the spectrum, does it? We can go beyond red. What is the wavelength region called that's beyond red?
Infrared.
Infrared. So if we really want to see the most distant galaxies, we should actually be looking in the infrared. And I will tell you the truth that these red dots here are all seen in what we call the near infrared. Okay, but we can do an infrared extension to the ultra deep field simply because in 2009 on servicing mission 4 we installed another new camera, wide field camera 3, and the science that we had to do with Hubble, the breakthrough science we want to do with Hubble was concentrated in the infrared. Okay, we've done visible light. There's still lots to do in visible light. I don't want to, get visible light astronomers mad at me. But the stuff we hadn't been able to do was in the infrared. This improved our infrared sensitivity. Okay, we had much improved infrared throughput, just like ACS was a jump over WIF-PIC2. WIF-C3 in the infrared was a jump over ACS. So then we could do long exposures, deep field exposures in the infrared, add it to the ultra deep field that we already had, and boom, we get the HUDF IR in 2009. And I will tell you that we did more of this in 2012, and we just did yet more of it in 2014. The results are similar to this, nothing quantitatively hugely different. What's the matter? What did my... Oh, I hit the button. That's what I did. There we go. All right. Wow. The blue is really funky in this. I have, on my remote, I can actually I can go forward, I can go backward, and I can blank the screen. Okay. All right. So the infrared actually shows us more things than we could see in the normal ultra-deep field. All right. And I'll tell you a few of them. In these boxes here are objects that could never be seen, that are not seen in the normal ultra-deep field. Matter of fact, you can see that there are just these small little blobby things here, all right, shown out in these highlight diagrams there. They're just barely seen in the HUDF IR. The previous ones had redshifts of 5 and 6, okay, and the larger the redshift, the further its distance. This one had redshifts from 8 all the way up to 11.9, okay? These are candidates for the most distant objects ever seen by any telescope anywhere, okay? But I have to say the word candidate. I cannot say they are actually galaxies seen at these redshifts, because in order to confirm that, we need to see them in multiple band passes. The light from these objects has been stretched so far that Hubble only sees it in its longest wavelength filter. Okay, the next wavelength filter doesn't see it. The longest wavelength filter does see it. Okay, and if you only see it in one filter, in your longest wavelengths, you can't call it a detection. All right, you shouldn't call it a detection. I will say that the astronomers who do this actually do call them galaxies. I, as someone who teaches, know that you can't do that. All right, you have to call them galaxy candidates. Now, there is probably a 90 to 95% chance that these are real galaxies, but we cannot prove it. To do that, we really need a telescope designed for the infrared. Now, of course, we have a telescope designed for the infrared up there right now. Does anybody know the name of the great observatory that observes in infrared right now? Spitzer, thank you very much. The Spitzer Space Telescope is up there. It does observe in the infrared, and the Spitzer Space Telescope can look at these galaxies. But the problem with Spitzer is it doesn't have the resolution of Hubble. Okay, it doesn't have anywhere near the resolution of Hubble. Okay, it's got a less than 1 meter mirror. Hubble's got a 2.5 meter mirror. Okay, in infrared you actually need a larger mirror to get the same wavelength resolution. So Spitzer can't confirm these. Spitzer can't pick out these individual galaxies. What we really need is we need a telescope, a space telescope with the resolution of Hubble and the wavelengths of Spitzer. Wouldn't it be cool to have one of those telescopes? All right, did you guys hear about it yesterday or during this week? You probably did. It is, of course, the James Webb Space Telescope. JWST will launch in 2018. This is a 6.5 meter mirror, almost 24 feet across. All right, it will have the resolution of Hubble in the infrared wavelengths of Spitzer, and it will be able to confirm whether these galaxy candidates are actual galaxies, along with lots of other really cool science, okay? So to go into the infrared requires us to wait for Spitzer for 2018. We astronomers aren't so patient, okay? Yes, JWST is going to be fantastic, and we can't wait for that, but we can't wait for that. We got other stuff we got to do. How can we extend Hubble's vision without waiting for JWST? Well, let's try using a lens in space. So, if we have a normal light bulb, and the light travels from that light bulb across the intervening space until it is observed by your eye, we consider it to travel in a straight line, right? There's nothing there to change it. But if we put a lens there, then the light from that light bulb can spread out. The stuff that spreads out can be redirected by the lens and brought down to your eye, and it can magnify, and it can augment it, amplify it, okay? It can amplify and magnify. Now, that's nice. Could we do that in space? Well, that would require bending light in space. But Einstein's theory of general relativity says we can do that, okay? Can anybody explain general relativity to me in 3 words? All right, at the end of this, you should all be able to do it. General relativity in three words: mass, warps, space. All right, this gentleman's been in my talks before, right? Okay, everyone say it with me: mass, warps, space. That's all you really need to know about general relativity. Okay, so in this animation here, if this is our flat space, and we have light from a distant star passing through, it will travel in a straight line. Now let's add the mass of a star and let that light come really close to that star. It will warp. The space is warped. A straight line through warped space is a curve. All right? Because mass warps space, it will also alter the path of light. Now, wouldn't it be cool if we could arrange to have so much mass there that we could make that light alter its course just like a lens? Well, that does happen, and not quite as cleanly as we'll show in this next animation. It does happen, and let me show you how. So the light from a distant galaxy, like the light from that light bulb, traveling across empty space between us, well, again, the null hypothesis is it travels on a straight line. Instead, if you put a huge amount of mass, say a cluster of galaxies, well, that cluster of galaxies warps space so much that it will deflect the light and act like a lens in space. All right? We have natural lenses in space that we can use to augment Hubble. How cool is that? Okay? Hubble is powerful, but Hubble plus the universe is even more powerful. So here is a cluster of galaxies, and then you see these streaky things here. All of these arcy, streaky things. What are they? Okay? Well, if we've got the cluster of galaxies here, okay, and Dave is now going to be Hubble, all right, and I'm going to be a background galaxy over here, all right, the light from this background galaxy goes through this warped space before Hubble sees it. And the light of this galaxy is stretched out into these strange streaky arcs. Okay? Gravitational lensing. Mass warps space, acts like a lens. Gravity as a lens, gravitational lensing. All right? And matter of fact, this is the image of a galaxy. This is the image of the same galaxy, and so is this, and so is this. The same image of the same galaxy's light passes 4 different ways through the lens, the gravitational lens, and is observed by Hubble. Really kind of cool. Okay? Plus, it doesn't just distort these images, it amplifies their light. Using that lens, we can see things that Hubble otherwise could not see. So in this image, we have 3, JD1, JD2, and JD3 are images of the same galaxy at such a distance when we estimate its redshift that it is so far distant and so faint that Hubble could never ever see it, except by using this natural lens in space. So we're using the lens of a cluster of galaxies to extend Hubble's vision into the universe. Now, wouldn't it be cool? Wouldn't it be really cool if we could take this Hubble deep field, one of the deep exposures with Hubble, combine it with a cluster of galaxies to act like a lens, and extend Hubble's deep field observations into the universe? So take that deep field, add in the cluster, and you get a lens deep field. All right? This is a simulation. All right? So this is the idea. Take your deep field, take your cluster of galaxies, center it on a cluster of galaxies, and you can see deeper into the universe. That, my friends, is the whole idea behind the Frontier Fields project, that we are going to use natural lenses in space to extend Hubble's vision. So what we're going to do is we're not going to use just Hubble. We're also going to use that Spitzer in infrared and Chandra in the X-ray to observe all of these cluster fields to see what we can see. We're going to look at 6 clusters. We have cluster fields, 6 cluster fields, all right? But we also are going to observe what we call a parallel field, because Hubble can do 2 things at once. It can walk and chew gum at the same time. All right? I sometimes can't walk and talk while I'm giving my presentations, but I try. So you can see the red boxes. These are the Wide Field Camera 3. These blue boxes are ACS. Hubble can observe the cluster with ACS while it's observing the parallel field in Wide Field Camera 3, and then it can rotate and do the exact opposite. Okay? So it's going to get both ACS and WIFC3 observations of both fields, all right, to enable us to do even more science. So we'll have the parallel fields. Here is the first results. Okay, we started this about 9 months ago. The first results we released last January. This is a cluster field around Abell 2744. You can see all the galaxies of Abell 2744, but you can also see these gravitationally lensed arcs. Okay, we're getting like the very last data on 2744 right now. We're searching this to see what objects can we see that we otherwise couldn't see. Can we find some of these really most distant galaxies? It's a very small probability that we'll get a large of them, but if we can get maybe 5 or 10 out of the whole project, it will greatly increase the statistics of looking at those deep galaxies. Furthermore, we're doing a parallel field. Now this parallel field, when you look at it, looks very much like a Hubble deep field. All right? But it's important that we have these parallel fields for the statistics, and I'll explain that in just a second. So with the Frontier fields, these cluster deep fields will use these gravitational lenses to see otherwise unobservable galaxies, but they will also be able to develop detailed gravitational lensing models of these clusters of galaxies. Because with James Webb, we will also be able to see things that Hubble can't see. And if we have the detailed models of how the mass is distributed in these clusters, we know where to look in these clusters to try and find the potentially most distant objects. All right? Again, if we do find these really distant ones, they're going to be candidates, and J2ST will be required to follow up to confirm them. Now, the parallel deep fields will increase the statistics. We've looked at the deep field. We've looked at the ultra-deep field. We've had a couple other places. But small number statistics hurt us. How do we know that when we look in this direction, the statistics we get are representative of the entire night sky? How do we know? We don't. Okay? We don't know. And this is what we call cosmic variance. The statistics in this direction, a very tiny beam in that direction, might be different from the statistics in this direction. We want to get lots of different skewers through the universe to try and see what are the global statistics. If we measure over 10 different fields, we have much better confidence in our statistics than we do if we measure over 1 or 2 or 3. All right? And right now we have about 4 directions on the night sky with good statistics. We'll have 10 after this. Okay? So this will allow us to really nail down our statistics. Okay, so let me finish with a movie. And I forgot to check if the volume is up. Let me just escape out of this to check. Turn the volume up. Hopefully it will come through the speakers. Okay.
For 2 decades, the Hubble Space Telescope has peered ever more deeply into the universe. From the groundbreaking Hubble Deep Field to the subsequent Ultra Deep Field and its infrared extensions, Hubble has revealed galaxies stretching towards the edges of space and time. Although further infrared exploration awaits the launch of the James Webb Space Telescope, researchers have yet one more trick up their sleeve. Einstein's theory of relativity explains how light, passing near a massive object, is bent by the curvature of space. A massive cluster of galaxies can act like a lens to gather and magnify light. This natural telescope of a galaxy cluster can extend deep field observations and help astronomers uncover fainter and more distant galaxies. NASA's great observatories, Hubble, Spitzer, and Chandra, have now launched an ambitious multi-year project called the Frontier Fields. A set of galaxy clusters will serve as gravitational lenses that probe to the ultimate depth of Hubble's capability, while a set of neighboring deep fields will diversify, enhance, and extend our studies of galaxy development. This community-developed program of cosmology research will examine galaxies in their earliest stages of formation and growth, providing a sneak peek at the first billion years of the universe.
I couldn't have said it better myself. All right, thank you all for listening. Okay, according to the schedule I have in my brain, I've got 3 minutes for questions if you have any questions on this. By the way, that video is available online to download if you are interested. What? Oh, Dan, look at us. We have to post this on Facebook, you know. Parallel universes, yes, okay. Although you're slightly more redshifted than I am. All right, questions? Any questions? Was I just so, no, I wasn't so, go ahead.
With the lensing, when you get multiple images, is there any way to sort of to get the original view?
Exactly, okay. So that's a really cool question. All right, so if you look at the lensing and you see these streaky, archy things, and you have, and especially if you have multiple versions of it, is there some way to de-lens it and see what the galaxy originally looks like? Yes, it's really difficult, and we don't get very good views, okay? And that's what talk about that cluster lensing models that the frontier fields will do. We're developing really highly complex models, and we can try to de-lens and see what the galaxy originally looked like. It's never great. So that's one of the reasons I do that simulated lensing, so you can see what the galaxies look like before the lensing and after the lensing, because that simulated lensing actually does the same calculation, but in reverse. Okay? So it actually takes the image from the deep field and then distorts it. All right? And so you could see how it changes. Yes?
Is space expanding uniformly, or are there regions where the redshift is more pronounced?
Okay, so is space expanding uniformly, or are there regions where the redshift is more pronounced? Space is assumed to expand uniformly. However, wherever there is mass of a galaxy, or a star, or heavy mass, that space is not expanding. Okay, the objects of those are not expanding. Okay, the space itself is expanding, but I cannot say that I'm getting fatter as I grow older simply because space is expanding. All right, I'm a collapsed object. I'm held together by chemical bonds. Okay, a star is held together by gravity. A galaxy is held together by gravity. It's the Milky Way isn't getting bigger because of the space expanding, okay? So up through clusters of galaxies, we have these collapsed gravitational objects, and the space within them, if you think about it, that those things are, you know, collapsed objects. But the space between, we sort of think of it as the space between galaxies getting bigger, okay? Which is why we talk about this as cosmological redshift, not any localized expansion of space, okay?